I attended several conferences of this kind, and this is the first time that we can enjoy 3 different topics into a single conference, which is an achievement in its own, I would say. So thank you about that. Second, you heard 2 talks about the sun as a gravitational lens. Slava Turishev, I think, made an excellent presentation of the physical optics of the sun as a gravitational lens, especially looking to imaging of extrasolar planets, which is, of course, the #1 goal that probably today we want to achieve. Especially, let me say, if the SETI astronomers discover some planet that shows signs of a potential extraterrestrial civilization. So here again, we have two different trends merging into a single topic. So my personal opinion is that if SETI succeeds in finding something interesting, then the space agencies will get some agreement, and finally some focal mission will be sent in order to image that planet very much in detail. But my talk is about a different topic, that is the use of the sun as a gravitational lens for telecommunications. Telecommunication across huge interstellar distances, of course. So since Avi Loeb asked us to be provocative, I guess I got it right, I have tried to comply with his request by putting the conclusion at the beginning. And the conclusion, in my opinion, is that when you go over to interstellar distances, I wouldn't regard laser communications as feasible. First of all, of course, because of the incredible angular resolution and precision in the pointing that you have, but also because of the powers involved and all that. So my suggestion is that if you want to establish interstellar communication, the best thing is to resort to radio telecommunication, but taking full advantages of not only of the sun, but of the stars as gravitational lenses. So I hope you don't mind if I'm jumping to one slide. I probably can come back to this later, but let me jump to this slide, please. Sorry about that. That's it. This is the message. We have been hearing one star as a gravitational lens, but we can do better than that. That picture shows 2 stars, specifically the sun and Alpha Centauri A, B, what you please, and 2 relay satellites on the opposite sides that I call focal spacecraft, just to give them the name, so that in conclusion you have 4 points that unfortunately have to be aligned very precisely. But if you can achieve this precision in the alignment, then you have a fantastic decrease in the powers involved for the telecommunication across interstellar distances. And this is the new result that I would like to submit to your attention. Of course, this is in line with the future development, because Alpha Centauri is the first system that we probably are going to explore, but there are many more. Pete Warden this morning was talking about other stellar systems. And now let me please take a bold step from the point of view of SETI. Now, I'm really glad that I'm talking to a SETI compatible audience, because in other conferences, you know, excellent engineering, spacecraft, whatever, when I came to this point, you know, the audience was shocked. What is this guy talking about? Well, here is what I'm talking about. We are discovering all this bonanza of stars as gravitational lenses just now, essentially in the last century. But who knows, in the galaxy there may be civilizations that discovered that long ago already. We are the newcomers, as it was said many times. So if you pick up this and that, you come to the conclusion that more advanced civilization than we are might possibly have established a set of radio bridges, this thing I call a radio bridge between 2 stars. So between every couple of stars, there is one radio bridge. So one, or a set of very advanced civilizations might have built a network of radio bridges, and just to give a name to all these things, I published a paper with the title of Galactic Internet. And you find it in Acta Astronautica. Now, suppose that this is the case, possibly nearby the center of the galaxy. I don't know, this goes into SETI questions. But suppose that this is the case. Then we draw a conclusion that as long as humanity does not reach capabilities of reaching the minimal focal distance of our own stars, we are cut off from the rest of the galaxy in the sense of SETI. Now, this is really profound, in my opinion. And this should be pondered over by the space agencies when the time will come, when the technology is good enough to exploit all this, as it was described by Slava and Lou Friedman. So that was the number one idea. Sorry if I jumped to this point, but if I had gone slowly through the slides, I would never have reached this, and you know, you would have missed the story. Now, let me go back, and this is just the usual story that Slava described, but this is just essentially the geometrical optics. Nothing difficult. You use the Schwarzschild solution. I should really mention that we should use better solution to the Einstein field equation, like the Kerr and so on and so on. Okay, now this is the key deflection formula, trivial things, you know the minimal distance, and this is the important equation. For whatever mass, not just the sun, there is an associated gravitational lens, and this is the focal distance of that thing. So it goes, as Slava said, with the physical radius of the sphere, of the object, squared over the mass. Now, if you reflect on this and you apply this to this solar system, you find that all planets have, each planet, its own gravitational sphere. So it's a set of spheres. And here are the results. They are not ordered as we know the planets are, because what really matters is what I described, that is this ratio. So the red thick circle is the Earth gravitational sphere. And this is important because when we will have the first interstellar mission going out of the solar system, when that spacecraft looks back towards the center of the solar system, of course, the planets move around the sun, so you would have a set of moving gravitational lenses. So this is once more a way to have magnified images of whatever lies on the other side. And that should be exploited, at least in principle, practically, to find many more magnified pictures, so as to say. Okay. One more point. This is the gain, and Slava already pointed it out. This is the Bessel function of order 0, telling you how much off-axis you don't have to go in order to lose the alignment. I don't want to spend more. This is a paper of mine about this set of focal sphere. And just to get the idea, I call the paper A New Belt Beyond Kuipers, a belt of focal spheres between 550 and 17,000 AU for SETI and science. Okay, but this was my book. I published that in 2009, but actually I should really publish one more updated edition because in the recent years there has been such a progress that this is already backward. Now, part 2, interstellar radio bridges. I gave you already the idea. This is a paper about that. Let me tell you more about using the sun as a gravitational lens for keeping the link, the radio link, between us and the first interstellar spacecraft going to Alpha Centauri. So this applies exactly to the case that was described by Pete Worden. And last night we heard about that. So I don't want to go through the mathematics, but the point is rather easy. The key point in the story is the bit error rate, meaning that what is the rate that you get a 1 if you send a 0 or the other way around? Of course, so you want to have perfect telecommunication or as perfect as possible. And just at looking at these graphs, the red curve is the communication link between the spacecraft and us if you do not use the sun as a gravitational lens. And the other one is with the sun as a gravitational lens. So you can immediately see that even just to go to Alpha Centauri, there is an abysmal difference, right? And these are, for instance, just to give you an idea, the parameters of Alpha Centauri A in terms of gravitational lens. So the focal sphere is slightly higher. It's 749 AU because, of course, the mass is larger and so on. Whereas if you consider B, it's slightly slower, but more or less is on the side of the sun. This is the radio bridge. Now, this is funny. This is an E that tells you exactly what is the advantage of using the radio bridge that I described for decreasing the powers needed to keep the link. So this is crucial for all nearby stellar systems. This is just the orange curve is just between the sun and Alpha Centauri A. But if you do the same thing for Barnard star, then you get, for instance, the two curves. And the moral of the story is that it all depends on what is the star on the other side. For instance, Barnard star is a poor star, so as to say, in terms of gravitational lens. And so it does not work very much for keeping the link robust. On the contrary, I didn't put the slide here, but if you consider Sirius, which is, of course, a very strong star because it has a much higher mass, even if it is much farther out, nevertheless, the bridge works better. OK, now, please let me convey a quote, crazy idea. I'm sorry, I don't have the slides here, but in my paper there is. Now, this is really new, but I want to convey to this audience because you are people used to bold ideas, as Avi was. OK, so I show you this curve, this knee, the orange one, OK? And then, just for fun, I said, OK, what's going to happen between galaxies, not stars, galaxies? OK, we know, in general, that at the center of each galaxy, there is a huge monster black hole. So, for instance, consider the Milky Way and M87, which is the center of our own cluster of galaxies. Now the black hole at the center of the Milky Way is something like 4 million solar masses, something like that. The black hole at the center of M87 is of the order of a billion of, so 6 billions, whatever. Of course, the distance is much larger, 60 million light years, right? So, for fun, I computed the same thing for that radio bridge. And the shocking result is that that radio bridge performs even better than the simple radio bridge between the sun and Alpha Centauri A. Wow, this was totally unexpected. So the morale you get from this is, can we have SETI in between galaxies? And my answer is, if those civilizations are capable of using their own big black hole as a gravitational lens, the answer is yes. With one advantage, that, for instance, if on a M87 there is a civilization exploiting that big black hole and sending messages towards the poor Milky Way, which is so far away, and so the beam is not too large, so as to say, we should be able to pick up their messages. But this is mind-boggling, also for SETI, not just for the gravitational lens, because we are coming to understand that there may be not only galactic internet, but a cluster of galaxy internet. Unbelievable. But this is what the calculation tells you. Of course, it's difficult to use the black hole as a gravitational lens, but that's another issue. OK, so let me finally go over to the last part. This is the paper. Now, this equation was shown yesterday by some speaker. And this is, of course, the capacity of a communication channel in the sense of Shannon information theory, right? The channel capacity. W is the bandwidth, P is the received power, and K is the Boltzmann constant, and T is the received the receiver's temperature. Now, that equations allows you to compute how much information can be sent between two stars or two galaxies in the sense that I described just now, according to physics. That is, there is an upper physical limitation beyond which we cannot go. And this is the simple limit of all that for, quotes, infinite bandwidth. That is, you have the limit of that thing for W tending to infinity. It's a trivial L'Hopital rules application. You get that. So there is an upper limit in the amount of information that can be conveyed in between the stars, if not in between the galaxies. Now, once again, from the point of view of SETI, this is mind-boggling, because we are at last putting our hands on the real physical limits beyond which we cannot go. Let me just plot this. The red curve, I'm reaching the end. The red curve is the channel capacity at the Ka band, just to take an example, at 550 AU distance, the red curve with the sun as a gravitational lens, and the blue curve with no sun, that is just direct communication. And you see the huge difference in the numbers, of course. More, the same thing applies to the different radio bridges between the Sun and Alpha Centauri A, the Sun and Barnard star, Sun and Sirius, Sun, and then a star equal to the Sun but located at the bulge of the galaxy, and just for fun, the Sun and a Sun-like star in Andromeda. And this gives you the limit, even for infinite bandwidth. So SETI has made here a step ahead, because we are now discovering at least a physical limitation beyond which we cannot go. This is the maximum amount of transmission we can do. And so, in the future, hopefully, we'll be able to, let me say, extend relativity in some sense. Not only in the sense, of course, that the speed of light is finite and so on, but also in the sense that communications takes time. And this gives you the numbers in the game. Okay, so conclusion. My suggestion for the mission that Pete Warden was describing is this one. We need to send two, not just one, two focal spacecraft. The first focal spacecraft is sent beyond 550 AU in the direction of the sky opposite to Alpha Centauri, either A or B as you please, say to 1,000 AU. Now this spacecraft would act like a relay satellite. So it would enable the communication between the Earth and the straight line going from the Sun to Alpha Centauri. And that is the number one. But that is not enough. Then you have to send the real interstellar probe that they called Focal 2, and that is, of course, sent again along the same straight line, but in between the Sun and Alpha Centauri. So the telecommunication link for that system is ensured by the Sun in between. Okay, now, it's not over yet. Let the spacecraft go, and sooner or later, don't ask me how long it will take, that depends on the propulsion, of course, but sooner or later, we'll get to Alpha Centauri. So the question at this point is, okay, what are we going to do with that? My suggestion is that we move it on the straight line between the Sun and Alpha Centauri, opposite to the Sun, on the other side, so we achieve the radio bridge. And that is absolutely the first necessary step for all the subsequent missions to come, because that will ensure the robust telecommunication between the solar system and the Alpha Centauri system just based on the radio bridge. If you lose that, then again you are in troubles because you need huge powers to keep the link. So this is the conclusion of the story. And the morale in 2 sentences is focus comes first, as Loeb was saying. And Interstellar comes second. And after that, I thank you very much for your attention.